Great. Welcome everyone to the Saturday space stream of Nexus Aurora. Nexus Aurora is a global aerospace innovation network with many Discord servers connected in our network. One of those Discord servers is of Vojtech Holub of Orb2, who will talk to us today. He has his own Discord server, and you're of course very welcome to join if you're in this Discord server during this stream. You can also ask questions below this YouTube live stream and on the different Reddit pages that we posted this live stream to. We already collected a lot of them, and we will do a Q&A after this great presentation that Vojtech Holub will give us. I would also like to say that people who are interested in joining Orb2 are very welcome, not only to join the Discord server, but tomorrow at 6 UTC on Sunday, the 6th of December, on this Discord server, there will be a big first meetup. So make sure you'll be there. And would like to give the word to Vojtech himself. And thanks for being here.
Thanks for having me. So, hi everybody, hi Discord, hi YouTube. So I'm here to present a space station concept, and let me make myself smaller so you can see it. So let me start with this render. It looks kind of ambitious, right? Well, my goal today is to convince you that it can be done, and that this kind of spherical concept is in fact a logical result of maximizing habitable space per dollar, while only using a single rocket launch and only proven technologies. This concept is called Orb2 because it's basically an orbital orb. In this presentation, I want to go through the reasoning that led me to this design, and I will explain how it fulfills all the required space station functions. But first, let me introduce myself. As Colin said, my name is Vojtech Holub, and I'm an R&D engineer working in image and signal processing. I also have a doctorate in steganography and of digital images, which is a really cool field that you should look up. So my daily job is not related to aerospace in any way, but that's where my passion is, and I guess a lot of your passions as well. Also, as a side note, this summer I started a small YouTube channel called Spaceflight Explained, which was very exhausting, but a fun ride so far. And I just want to note here that the presentation that I'll be showing today is a modified version of a talk that I gave at AIAA SciTech conference in 2020. That was when attending conferences was actually a thing. So what is the motivation behind the Orb2 concept? When we think about the future of space colonization, we often imagine vast space structures such as large rotating O'Neill colonies, but what we have today is the International Space Station. Don't get me wrong, I think it's a marvel of engineering that can accommodate 6 people and has been continuously occupied for almost 20 years now. But when you look at it, it seems very far away from our idea of the future. When you look at the difference, it's obvious that there are many steps and technological advances that are required before we can even consider building structures on such a massive scale. So the goal of this concept is to fill in the first blank, the first step, by creating much cheaper and larger habitable space in space. This concept, the Orb2, could be used for in-space manufacturing, research, accommodations, or space hotels. Or even, So the question is, why does ISS look the way it does? What you see here on the picture is the Space Shuttle Discovery, and it carries the largest ISS module cable within its cargo bay. The cable is 11 meters long, 4.4 meters wide, and around 150 cubic meters of pressurized volume. So as you see here, the Space Shuttle is packed, and as a result, the size of any ISS module is limited by the cargo bay of the Space Shuttle, or payload fairing of the largest vehicle available. As a consequence, ISS consists of connected small cylindrical modules. This approach comes with disadvantages. First, the lack of large continuous space. This might not be a problem for research on ISS and the hardened NASA astronauts, but If we want to start manufacturing or luxury accommodations, it might become problematic. The second problem with this is a more fundamental one. The space station built from small cylindrical modules will have a low volume to surface ratio, resulting in large surface area. With more surface area comes more mass in pressure walls and the micrometeorite and orbital debris shielding, which directly leads to higher costs in manufacturing and launching. So what changed in the last 20 years that allowed us to think differently? Mainly the near future launch capabilities. In 2021 or 2022, there should be 2 new heavy or super heavy lift vehicles on the market. One is the Blue Origin's New Glenn, and the other one is SpaceX's Starship and Super Heavy. Both have 2 major advantages compared to the rockets of the past. They will be partially or fully reusable, therefore lowering the cost per launch, and both will have humongous payload fairings. Now, even though Starship will probably offer more payload capability to low Earth orbit and larger fairing, its specifications, like detailed specifications, are far from being finalized. The New Glenn, on the other hand, has a very detailed payload user's guide, which is available, which contains the information a customer would need. Because of this, the Orb2, this concept, is designed specifically with New Glenn in mind, just because there is more available information, specifications that you can design the space station for. That being said, if Starship would be less advertised, and you would design Orb2 to be carried by Starship, the pressurized volume would roughly double. Now let's look at the New Glenn's capabilities. I know that Starship is all the rage today, but New Glenn will be amazing in its own right. It's designed to be 7 meters in diameter and overall height of 96 meters. So that is only 15 meters less than the full stack of Saturn V. Its payload to Earth orbit is either 37 tons with the high capacity payload adapter that they offer, or possibly 45 tons if the customer provides their own. This is not exactly clear to me. But what is clear to me, though, is that the New Glenn will have the largest payload fairing ever flown, with a possible exception of Starship. At 87 meters. So let's look at the payload fairing here in detail. So these figures are taken from the New Glenn's payload user's guide. The left figure describes the inner diameter of the payload fairing at different heights, but I want to focus on one number here, which is the 6,350 millimeters. So that's the maximum radius that you can fit inside the payload fairing. The figure on the right shows the maximum distance from the adapter interface plane, which is down here, of the center of gravity, based on the different payload mass. So generally, the heavier your payload is, the closer, the lower the center of gravity has to be. Assuming that we operate with the maximum allowed payload mass, which is here the 37 tons, the center of gravity must be less than 4 meters from the adapter plane. You have all the available height of the fairing, but your center of gravity has to be here or below. So let's remember these 2 constraints, the maximum width and the required low payload center of gravity, as I move this presentation in a slightly different direction. Sphere. So why would you want your space station to have a spherical shape? Well, we all know that launching heavy things to space is very expensive. Cost of SpaceX's Falcon 9 is from $3,000 per kilogram, and that's only if you fill it up the brim. And generally it can be well above $10,000. Space station pressure module walls are heavy because they serve dual purpose. They hold the air pressure and they provide the protection against micrometeorites and orbital debris. The more walls you have, the more mass you need to lift, which increases the manufacturing and launching cost. What you need is a shape which minimizes the surface area for a given volume. And as you have already guessed, that's a sphere. And the sphere is also an ideal pressure vessel, because of the uniform distribution of the stress forces in the sphere. It requires less material, which again lowers the mass and the cost. All right, great, but our hypothetical space station needs to fit into the payload fairing. So similar to James Webb Space Telescope, it needs to be segmented and packed in order to fit. Now, there are many ways how to split a sphere into smaller segments. What we can do is to specify few requirements and then select the method that fulfills them best. So let's start with the ease of manufacturing. It makes sense to want as few unique segment shapes as possible. If every segment is shaped differently, they would be more expensive to make and they would not be interchangeable with each other. We can use the same reasoning, and we should require the segments to have some symmetries. The space in the payload fairing is limited, and the flat-packed segments should make good use of it. If we exclude weight considerations, the better the fill factor of the payload fairing is, the larger the space station can theoretically be. And the last but not least is the ease of assembly. The resulting segments need to be aligned perfectly, and that would be easier if we minimize the number of edges that meet at each vertex. And this is a vertex, and there are 6 edges coming to it. So we want to minimize the amount of edges coming to each vertex, because then you would have alignment problems. So the image on the right here is an example of a sphere segmentation, but it's a rather poor one. So let's look at the segmentation method I believe is the best. So there is a family of geometries called Goldberg polyhedra. There's an infinite amount of them, and they consist of many hexagons and always 12 regular pentagons. This concept, as I presented, focused only on Goldberg polyhedron 1-1, which is this middle shape here. Otherwise known as truncated icosahedron, or as most of you know it, the sucker ball. For multiple reasons, is the largest Goldberg polyhedron that can be used with the new GLAN. It consists of 32 segments, 20 hexagons, and 12 pentagons. They are all regular, rotationally symmetrical. But as you can see, there are only 3 edges meeting at each vertex. So that's pretty good. And the payload fairing utilization is much better than in the previous triangular example. So if you assume that the green circle here is the payload fairing diameter, you can fit the hexagons like this and pentagons like that. So you get a pretty good fill factor there. All right. So until now, we described the capabilities of New Glenn rocket, the payload fairing space, and the method of splitting a sphere into 32 smaller segments. So with this in mind, how can we create a functioning space station, pack it into the payload fairing, and then assemble it in space? Well, now the fun begins. The picture on the left here is the Orb2 in its launch configuration with the New Glenn's payload fairing. Remember how one of the requirements was to have the low center of gravity? So it can be achieved. The heaviest 20 hexagon segments are here on the bottom, and the 12 pentagon segments above. When doing the math, it turns out that each segment thickness has to be at most 15 centimeters thick. The cylindrical structure on the top of the stack is the service module, which is launched already fully assembled. The picture on the right, this whole picture, shows the space station in the mid-assembly state. You see the solar arrays rolled out, and part of the segments is already put in place. I will go into more detail soon, but these 2 images should give you a good idea what the concept is all about. So now let's look at Orb2 in its fully assembled state. And here it is. Note the human force scale. This space station then consists of 2 basic modules, the large spherical habitation module, which is empty when assembled. In the renders, the hexagons have decently sized windows in the center, so when you see a window, that's the center of a hexagon. And then there is the cylindrical service module, on which you can see the solar panels, radiators, and potentially it houses assembly arm. So this is the image. Let's look at the numbers. The most important number here is the pressurized volume of the habitation module. So just the habitation module, the sphere. which is over 2,000 meters. That's the double of pressurized volume of the whole International Space Station. The mass of it, based on the basic CAD models, is roughly 24 tons. The inner diameter of the module is 15.6 meters. And when we go to the service module, it's more of a placeholder. But the available mass for New Glenn is 13 or 22 tons for the service module, depending on the payload adapter system that you choose. The diameter of the service module, as visualized here, is 4 meters. As the solar arrays, as visualized, should provide roughly 40 kilowatts of power. And between the service module and the habitation module, there is also a hatch. So, a crucial part of any space station is its protection against micrometeorites and orbital debris. All, I'll call it MMOD. All MMOD protection designs currently placed on ISS are different variations of so-called Whipple shield. Whipple shield, instead of making the pressure wall much thicker to resist the micrometeorites and orbital debris, this would add a lot of weight and mass. Whipple shield uses so-called Whipple bumper, which is a thin sheet metal placed at some distance in front of the pressure vessel. Then, when bumper is hit by the projectile traveling many kilometers per second, it does not stop the projectile. The bumper does not stop the projectile, but it fragments the projectile, and consequently the energy of the hit is distributed over much larger area of the pressure vessel instead of a single point that would get penetrated. An improved version to this is called stuffed Whipple shield, and it adds multiple layers of ballistic material between the bumper and the pressure wall to better catch the debris and spread out the energy more. There are many great resources publicly available on the design of the Whipple shield, but I decided to make it as safe as possible. So I looked at all the configurations on the International Space Station and picked the one that's chosen only for the most exposed, most critical parts of the International Space Station. So this is the heaviest configuration that you will see on ISS, and I put it all around the sphere. This configuration is designed to stop 13 millimeter diameter aluminum sphere traveling at 7 kilometers per second. You can imagine that this makes Orb2 very safe, but also quite heavy. So going from the inside layer to the outside, the first layer is the actual pressure vessel, which is 4.8 millimeter thick aluminum 2219 in the T87 temper. Then there are stuffed layers, which consist of 6 layers of Kevlar and 6 layers of Nextel, which serves as a protection against thermoshock and ballistic protection. Closer to the bumper, you have the regular multi-layer insulation for heat insulation. And finally, there is the 2 millimeter thick Whipple bumper, which is usually made out of aluminum 6061. The total thickness of this sandwich is 12 centimeters. So it is smaller than the required 15 millimeters to be able to flat pack it into the payload fairing. These are the drawings of the hexagons and pentagon segments with the Whipple shield and all the important numbers. Hexagons are on the top, the left drawing is outside view, the center is the inside view. You can see the ISO grid, and the right drawing is the side view. Note that the largest dimension here, the 6300, is determined by the inner diameter of the payload fairing. So again, there are 20 hexagons with mass of 850 kilograms each, and 12 pentagons with mass of 600 kilograms each. So this is a mass of the structural material only, the Whipple shield only, and the pressure vessel and the MLI, the multi-layer insulation. It does not account for any wiring, plumbing, and other things. If you add these segments up, it amounts for 24.2 tons. So that's a slightly optimistic number, but again, it can be lowered by just making the Whipple shield a little bit less like a tank. Design process, my main concerns were the tremendous forces caused by the inside atmospheric pressure. I was worried that the walls would require so much structural material that it would become too heavy. 1 atmosphere is 1 kilogram per centimeter squared, so the total pressure applied on the single hexagon segment is roughly 260 tons. Luckily, the spherical shape helps a lot. I used 2 ways of assessing if the segment can hold the atmospheric pressure, but both methods are only approximations. The first method is based on a thin wall approximation for spherical pressure vessel. This formula gives you the maximum atmospheric pressure based on the material's yield strength, wall thickness, and the sphere radius. This approximation does not account for the isogrid strengthening or anything like that, but it tells us that it can hold, this pressure vessel will be able to hold 4 times the standard atmospheric pressure. The other way I used was finite element analysis on the CAD model that I created. It's also approximation due to the imperfect boundary conditions that I have there, but the analysis suggests that the highest stress for 1 atmosphere would be only about 28% of the material's yield strength. In either case, there's a lot of margin for dealing with the atmospheric pressure in the habitation module. So until now, I focused mostly on the spherical habitation module, but this concept would not work without the service module. It would be built as traditional cylindrical module, but with pentagon-like piece at the end, which contains the hedge to the habitation module. The service module can weigh, as mentioned before, 13 or 21 tons, depending on the payload adapter system for New Glenn, and it has to provide all the functionality required for space station, which might be very challenging, because this functionality includes environmental control and life support system, solar panels, radiators, docking ports, communications, attitude control, ion thrusters, housing for the assembly arm, and possibly more. In other words, while the habitation module is designed to provide a lot of pressurized volume, the service module has to do everything else. And sorry, got stuck here. Yes, so on the previous slide, we described the habitation and the service module, but I still did not explain how to put all this together from the flat-packed launch configuration. So I think it's time to describe the important part of this concept, and that's the assembly and welding arm. The assembly arm has dual role. It needs to pick and move and align the wall segments, and then weld them together using electron beam welding method. I'll talk about that further. It seems like a very difficult task for a single arm, but there are a few things that make this much easier. First, the whole process takes place in low Earth orbit in 0G, so the arm can be very weak and slow, and if it takes months to build, that's okay. It can be either semi-autonomous or directly controlled, which is possible because of the low latency in low Earth orbit. The inner pressure wall has to always include some sort of a latching plate that the assembly arm can grab onto and get electricity through it as well, and controls. For welding, you would need roughly 8 to 15 kilowatts of power to be able to weld these segments together, sustained at a few minutes at a time. So I don't think that's an impossible number, 8 to 15 kilowatts. The solar panels can easily provide that. So let's talk about electron beam welding, because that's what makes this concept viable. So the electron beam welding is a surprisingly mature welding method developed in early 1960s. It uses a beam of high-velocity electrons focused and applied to a very small area of the joint. The electron's kinetic energy is transferred on the material, which melts and fuse together. There were several low-power tests done by Soviets in the low Earth orbit. The first one was Soyuz 6 in 1969. After the breakup of the Soviet Union, NASA was sent few samples, and they concluded that it's as good as any Earth welds. By the way, one of the most famous and complex uses of electron beam welding was for the F-14 fighter jet, where this method was used to weld the wings to the titanium wing box, the wing carry-through structure, which transfers all the loads from the wings to the fuselage. So let's look at the properties of electron beam welding. Starting with the first one, the welding process requires high vacuum environment, otherwise the electrons will be dispersed by the air molecules. This requirement is the main reason why this method is not used more and is only limited to very few specific applications. Any Earth-based electron beam welding system needs a vacuum chamber, which makes the device very expensive, and the mass production would be very slow because you have to evacuate the chamber every time. But this property is perfect for welding in space. The electron beam welding is autogenous only, meaning that there is no filler material, no welding material needed to be added. It simply works by melting and fusing the workpieces. It works best on the square butt joints, which I try to visualize here. Simple joints that I just put together and welded from perpendicular directions. And also, electron beam welding offers an incredible control of power and weld depth, purely by changing the electric fields by software. And it can weld materials from thicknesses of a fraction of a millimeter to over 30 centimeters of steel. So you can have a 30 centimeters deep weld. Also, the welding speeds can be very high. Moreover, you can weld you don't have to be close to the welded piece, you can be up to 75 centimeters from it. And finally, a very important for space-based welding is the efficiency, which is for electron beam welding around 95%. That means that only 5% of the input power is converted into heat within the gun. So that has one major advantage that allows you to cool it down easily. But it also has one disadvantage, and that is that welding emits strong X-rays. So for human welding, the power must be significantly limited because it would mess up your astronauts. So I think that these properties are so favorable that I believe that robotic electron beam welding in space has to play an important role in the future of space exploration. And finally, this is how the assembly process would look like, step by step. The first drawing on the left shows the space station still attached to the second stage of the rocket, but after the payload fairing was dropped, the image A. After the second stage finishes its burn and places the space station into a stable low Earth orbit, it detaches, solar panels roll out and provide the power. An assembler robot leaves the housing and starts assembling. In C, the assembler robot starts to pick up the individual hexagons, aligns them, and latches them in place. Due to the hexagon's side profile, the robot has to align the hexagon from the outside. For image D, the hexagons are all placed and only the holes for the pentagons remain in the stack. The side profile of the pentagons allows them to be inserted from the inside. And when segments are in place, the robot welds and all the joints the robot has to weld all the joints, so that's a long process. And it can do it very slowly and can take pictures of the welding process, X-rays, and all that quality control stuff. And once you're done with this sphere that's assembled and welded, you can start testing it. You can start slowly increasing the pressure, see if it leaks somewhere, fix it, and you can slowly increase the pressure all the way to 1 atmosphere, and then you're done. You have a huge empty space, and now the astronauts have to arrive or kind of set up crew to make the habitation module habitable and do kind of all the plumbing that's required by the customer and fit in the rooms for the hotel and things like that. So I have a great rendered video of the full assembly process, which is a little bit over 2 minutes long. So we will try to play the video and see if it works. And if it doesn't work, if you go to the www.orb2.com, it's going to be right on top. It's on YouTube, so you can play it. We'll try. Adrian?
Yes, Adrian is showing it on the YouTube live stream, so we're gonna watch it now.
Thank you very much. So I hope you liked it. And yeah, this is pretty much it. I know that this project is ambitious, but I hope that I convinced you that this can be done today with today's technology. So to summarize this, we have a concept that with a single launch of New Glenn or Starship, using proven materials and technology from the International Space Station, which is assembled by a robotic arm equipped with proven welding method. So this concept offers twice the habitable space of the International Space Station, and if it was designed for Starship, it would probably offer 4 times the habitable space of the International Space Station. And if I can put a shameless plug here, if this concept seems exciting to you and you would want to help bring it closer to reality in your free time, please contact me at Orb2 at Orb2.com, down here is the link, or my personal email, Vojtech Holub at yahoo.com. You can also go to the Orb2.com website, and right on the top you'll have a Discord link that you can use to Nexus Aura and Orb2 Discord servers. So anyone with engineering, manufacturing, CAD, machining, interior design, web design, or life support knowledge would be great help.
Will want to join, and they can do that indeed on the orb2.com website, but also below the YouTube video that we are streaming this content to right now. So thanks so much for the clear and concise presentation. It's really good, and the interesting thing is that we have a lot of questions. I'm gonna take a look at my monitor, and we're now at already 5 pages full of questions. So that's great. Yeah. No worries. Yeah, I'll do it quickly. There's the whole idea behind Nexus Aurora is that we are a network actually in which we can connect people between each other, and you can showcase your project. So don't feel bad about plugging your Orb2 project. That's the whole idea. We want to bring people closer together and get space projects off the ground. In this case, it would be really great if we could actually launch this one day on a New Glenn or Starship or other rocket. We have had a lot of questions, so I'm just going to dive right in. And I must say that there are some very good ones in there, and there are also a lot of people who just react and explain how really cool they think this project is. So you're going to get a lot of compliments as well. I'm going to tell you that already.
And before we go to the questions, I don't know if the viewers could hear. If you go to orb2.com, on the top of the website, there's a link to the Discord channel that links to the server that we will be kicking off tomorrow. So if you want to join us and hear what we have to say, and you would want to be part of this, please join us.
Absolutely. Yeah, good that you say that again. I'm going to start with a compliment by someone on Reddit, on the BMA's subreddit N104CD, and he says, I love this concept and I wish you luck in seeing this come to fruition. Which I think a lot of people watching this will feel the same about. Then on the Nexus Aurora subreddit, Mr. or Mrs. TC Torrent asks, this is insanely cool. That's the compliment at first, of course. And then would the business case be to R&D, manufacture everything in-house? That's the first question. And the second part of that would be, would you lease to Blue Origin or potentially SpaceX, or operate these independently?
So to the first part, the business question here is part of what makes me so exciting about this, because the way it works, kind of all the pieces fit together in a way that could be mass-produced somewhat. And to me, like this concept actually could be profitable. Of course, there is so many millions of dollars that would have to go to R&D and manufacturing. But yeah, I think the business concept here is I would compare it to a construction company. It's like, we'll build your warehouse, we'll build your house. How you equip it is up to you. You'll do the piping, the walls, and then the rest is on you. So that's kind of the business part of it, how I see it. And to the second part of the question, I would work with whoever wants to make this real. Now, we need to work on making it happen.
For sure, yeah. That's also why this talk is so interesting, at least to me. And I'll be joining the Discord server for sure to keep an eye on the progress and also contribute to it, maybe even. So the next question is from Mebot on the space exploration subreddit. Is the construction arm moved to an external location after construction is completed? And is there expandability available to this station?
Okay, sorry, I had some noise in the I don't know what happened.
Yeah, I'll say it again. So the construction arm, as you showed in the movie.
No, I'm sorry. I understood. I understood. It's just my earplugs did some noise, and I didn't know what that meant. Yes, the robotic arm, once it's finished, because it assembles the whole station from the inside, it will be left inside, which can be later dismantled by the astronauts or sent back home or used for, in case of emergency, right? If there's an emergency, something happens to the habitation module, the crew would go inside the service module and could use the arm to inspect and fix things.
You could say
that was
maybe,
the second part of the question.
Yes. If this could be an expandable station concept, so multiple ports and docking adapters, for example. Can you talk about that a little bit?
I think so. That was in my mind somewhat. This concept was initially made to be as simple as possible to work, like kind of the minimum viable concept that would actually work. But you can imagine that the service module can have many different attachments and you can assemble whole complexes out of these. It kind of makes sense because the main be expandable. You can make it bigger by launching it in bigger rocket, but that's about it. But you can connect multiple together through the service modules, and then you have a bigger station.
Yeah, and there might even be options, I would say myself, to create multiple attachment points to the orb itself, right? Because, for example, now you showcased that there are windows on each hexagon, if I remember correctly. Those potentially could be panels that could connect to a different orb in the future. And one other thing that is maybe interesting that someone asked about as well is the ways that the space itself could be divided up, because now it is a pretty large diameter. And of course, in space, you have to be able to touch some walls. Otherwise, you're going to be stuck having to wait a few minutes to reach the other side of this great large orb. Can you maybe explain a little bit about how that could work?
Absolutely. Again, I would compare it to a warehouse. You come to a warehouse, it's totally empty. And whatever the customer would want, they can, it's not such a problem to divide the space, especially if you can mount things. If the segments are made in a way that you can screw hard points, has some hard points so you can screw things into them. I don't think that dividing a sphere is such a problem, especially in 0G, you can do pretty much anything you want. And of course, initially, I can imagine that the initial crew would have some fears and issues of being stuck in the middle. But also, as astronauts on ISS proved, you can kind of swim your way away.
Yes, that is true. But as you also said, I think this is like double the complete internal volume of the ISS. So this is a pretty big thing. Then a question of my own, before I continue to the many other questions, would be how the interior itself would be built up. In this case, would that be sent up in the same launch, or would that be in separate launch?
The idea right now is that it would be totally separate. So if there was a company called Orb2, they would set up the sphere for you, so it has atmosphere inside, life support, but it's totally empty. And then, based on what the customer wants, you could have a service that here is a cargo delivery with some assembly crew, and they would put together your interior. So that would be a separate launch with both the crew and the equipment needed for the inside, or potentially multiple launches.
Yeah, that's very clear. And maybe the biggest challenge would be to find a way to do it all in one launch, if at all possible. Maybe larger payload volume like Starship would help in that regard. But for now, the fact that you choose the Blue Origin New Glenn rocket is a clear reason why you chose this, I guess. So I'm gonna go give you some compliments from guys, because there are a lot of compliments as well. Kavalt on the space subreddit says, he actually says that the arm should not fall off, but because then you have a big problem. But another compliment would be that that the ISS is going to look like an overpriced toy in just a handful of years if we can keep developing these kinds of great ideas. That was said by a gateway note on the SpaceX Lounge subreddit. And
if I can comment on this,
again,
I think that ISS is wonderful, but it's all designed with the capabilities that were available in 1970s and 1980s. So for the time, for the technologies, they used only proven ones. So it's amazing, but if we can streamline it the way SpaceX does with the rockets, then we might have something on our hands.
Yes, we are all rooting for this easier access to space with all of these incredible companies working hard on that. Then one other thing that is said here is that the Leech-style robotic arm is incredibly clever. That's by Vince Samios on the aerospace subreddit. Just a compliment before we get to the next. Yeah, for sure.
Yes. Yeah. Actually, it's not my idea. The Canada Arm 2 on the International Space Station is a walking arm. It can walk over the space station from the latching point to latching point. And also, I don't know if it was shipped yet, but European robotic arm for the Russian part of the space station has the same capability. So it's not new, which makes me happy because there's no R&D needed really. It's been done.
There might be some R&D needed for the actual proven welding in space. I know that you said that I think the Russians did it, but in this case it has to be, of course, completely fault free. And I have one question specifically about that. which I will try and look up who asked it, but it is about, is there any way to maybe compartmentalize in the future a part of the orb if, for example, there is going to be a leak at some place?
That's a really great question. And initially, to make things simpler, I just think of the service module as kind of second compartment that's big enough and will have the light support to actually be that kind of the safety net there, and also the docks. So if something happens, the crew can just go there and leave. But yeah, definitely it could. There would have to be a bunch of engineering to make it viable because the pressures are so high. So to make it structurally sound, it would not be an easy task, but something that could be definitely looked into.
And another question would be that the service module itself seems to have one entrance point at this time, right? One hatch towards the orb. Is there also a hatch on the other side?
Of the service module?
Yes.
Currently, that's the place for the ion engines for the station keeping and keeping the orbit. So
that's pretty,
you have the ion engines.
That's very logical. But because of all the other questions about sort of expandability, well, it's something that we can talk about later on the Discord server as well. That there are so many options when you try to get an extra port.
I apologize for the noises.
No worries. And then in the future, because this is such a cheap method, and that you can add multiple stations to this, that could be really cool. If each launch gives you double the ISS volume of extra capacity, that's really, really great. Okay, so someone who is new to Reddit, because that's his username, on the Be Amazed subreddit asks, I have a dumb question maybe, but could something like this be used to make a larger, more long-term space station? That's it? What do you think?
I think it's definitely larger, and the goal is to make it long-term. So I hope so. That's part of the goal. And by larger, if the idea is to have it 10 times larger, order of magnitude larger, it would be possible if we figure out the way how kind of to, like, what is this? This is just a bunch of flat-packed segments together. If you can launch enough of them, even in multiple launches into space, you can build something much bigger.
Yeah, for sure. Then one compliment from Shupak, and that is actually the fact that he says, why has this not been done already? It seems so logical, like an IKEA flat pack idea. He is in at least, and he says robotic arms are already a mature technology, as you said, with the Canadarm as well. I'm just going to remind people while trying to read all of these questions coming in, that people can still keep asking questions. We'll be continuing this Q&A for a while. Even after this whole Q&A is over, people can also join our Discord server right now on Nexus Aurora and actually join the meeting that when we stop the stream itself, we will keep continuing this talk with Vojtech himself, and you can actually ask him in person questions as well, just so you guys know. I'm gonna take, and if there's anything you would like to talk about specifically about the Orb2 concept, and maybe when you started thinking about this concept, that would help me find the next question.
Yes, so roughly 2 years ago, I was thinking like how to kind of create a space station that was kind of out of, let's say, somewhat like Lego bricks, like pre-assembled, pre-made pieces that you would just put together in space and create something larger and efficient than the International Space Station. And it took me definitely a few hours of thinking before I realized kind of the soccer ball geometry that's kind of the perfect shape. So then I couldn't sleep very well for the next few days, and I was just started working on it. And my goal was to just get it far enough to realize why this would not work. So my whole goal was to realize why it wouldn't work. I couldn't find it out. Wrote a paper for a conference, hoped they will tell me why it doesn't work. It was accepted. I talked to a bunch of people, presented at the 2020 AIAA conference. Everyone no one, even like professionals from NASA, didn't tell me why this couldn't work. Of course, they had a lot of very small technical details that this could be a problem, this could be a problem, but it was very kind of, you can engineer your way around these things. And then let's go further, let's write a journal paper and see if the peers will criticize it. It got into the journal. So right now, after 2 years, creating the renders and everything, here I am still trying to find a reason why this wouldn't work. And I think it's time, the time has come to actually try to make it work.
For sure, that's like the scientific method in that case, of course, which you are familiar with, to really try even to disprove your own ideas. But in 2 years, you haven't managed to do so. So congratulations on that in the first place. I'm going to ask a question asked by a space instructor, and that's about the 1 atmosphere of pressure. Is that mandatory, or could we create lower pressurized habitats? So, for example, is the ISS also 1 atmosphere? And is that mandatory?
Oh, that's a good question. Definitely the US part of the ISS is 1 atmosphere. And I know that the actual Russians always had 1 atmosphere. And for Apollo, United States tried 20% or 30%, just the oxygen atmosphere. So that is lower pressure, but as much oxygen. And that didn't work out well for the Apollo crew, the Apollo 1. So generally, it's a good idea to have kind of similar atmospheres we have here, because it prevents kind of flash fires and burnings, and we need certain amount of oxygen with every breath to take in. So generally, especially if you want to make this available for common folks without much training and risk management, 1 atmosphere, I think, is the way to go.
Yeah, if you don't want to have an altitude training before going into space, that would be better. Even though there are some negative consequences in the structure, because there's a lot of pressure and a lot of forces on this shape. But as you also said, of course, the spherical shape is the best shape to actually make sure that it stays intact. I'm going to ask a question now sent through YouTube by Willie956, and he asks, or she asks, how confident are you guys of New Glenn reaching orbit in 2021 or 2022? Because, of course, that's what you started your presentation with.
So their original deadline was end of, 2 years ago, a year ago, their deadline, or their hope was end of 2021. And right now, I believe it's the first half of 2022 or something. So for space rocketry term, they didn't postpone it too much so far. So I think they can make it till the end of 2022. I believe them.
You believe, yeah, that's good. Yeah, they're creating some really cool infrastructure, and even though SpaceX gets, of course, a lot of the hype, and because they have so many rockets launching as well, and over 100 Falcon 9 launches at this moment. Let's just say that with you, I positively hope that Blue Origin will surprise us with this really awesome rocket on paper, at least, and make it into reality.
Yeah, SpaceX needs a competition, definitely. And,
for sure.
Unlike a totally different philosophy, like the first launch they make will be fully operational. So such a different philosophy than SpaceX is. So we might see Starship flying very soon, but it will take time to actually take commercial cargo into orbit.
Yeah, and I think Blue Origin actually created some great fairings, and they have showcased that they can actually do that. Or for your design. I'm going to go to a next question on YouTube below our YouTube stream, and that is asked by Theodore Nordseek. Do you think there's a chance that New Glenn will eventually get a 9-meter fairing? Or at least, like, I would say, comparable to Starship?
I'm the wrong person to answer this. It definitely isn't public if they're thinking about that. And as I mentioned, the current New Glenn's payload fairing, they abandoned the smaller one, so they just stuck with the bigger one that they thought about. And it's 3 times the volume of the Falcon 9s. So it's not small.
It is very big, that's true. And you showed it as well. A lot of questions coming in through YouTube, so I'm just going to go and ask some of those. About the atmospheric pressure, Jonathan Clayton asks, would flat isogrids rather than curved isogrids make any sense?
That's a great question. Assuming that you mean the segments being, instead of being part of the sphere, being flat and then assembled. That was my first design. And then I was happy that I did the CAD modeling, because it turns out that the forces in the connections and where the angles are incredible. And that's something I couldn't find my way around it. So physics drove me to this curve design, even though it's way harder to manufacture, I'm sure.
Yeah, because exactly that was the response by Jonathan himself as well, that he says it would be easier to manufacture without the double curved surfaces, of course. Then Joshua Perry asks on YouTube who the target customer would be. You talked about it a little bit. You would say anyone willing to make this into reality, but who would you think would be the most likely customer, maybe?
I'm not sure. By customer, you mean a person who would build this, or a person who would pay for this to be built?
I would say the latter, but Joshua can maybe respond in the YouTube comments if this answers his question.
For me, if I was pitching this to investors today, I would just show them the prices that rich space tourists are willing to pay to get to orbit. I think the current price is $60 to $70 million for a 2-week trip. If you can make it efficient, if the launches become much cheaper, there is enough base to make 1 or 2 space stations pretty profitable, I would say. So to me, easiest to quantify would be space tourism for Baltic, unfortunately. But that would drive kind of the routine, the costs down to think of other places, other uses.
Yeah, there's a question by Theodore Nordseek again, and that's about something that you have explained but was not clear to him, I think, about the hexagons that they... he thought that it would be placed together from the outside, but how does the last hexagon get placed? Can you explain that a little bit?
It's doable. So the hexagons do go from the outside, but when you are placing the hexagon, you still have the hole for the future pentagon next to it, so you can kind of be a little bit kind of bend it outside and stick it into it.
Would you actually say?
I have a 3D printed model of this, so I was making sure that it can be done.
It actually works, yeah. And would you say that there would be absolutely no need for human intervention in the whole project, or would you say that there would likely be some help involved by humans before it gets to be a pressurized volume? I mean,
I definitely would not recommend humans being there before it's pressurized or during the pressurization. I think if we can avoid human intervention there, then the whole thing becomes much less risky. And right now, I don't see a reason where they could be helpful. And if it fails because something is missed, then that's a lesson learned. Definitely the humans would be still in like very close loop remotely on Earth. Because you're in low Earth orbit, you can control things differently, you can do things very slowly, get a very good view of each weld before moving on, passing the pictures to the experts.
Yeah, that's pretty logical. Then we have a question by Sean Wessels on our Discord server of Nexus Aurora. He asked, did you take a look at creating smaller diameter, it says cylinder, but I think he means sphere, and because these lower pressures could mean lower material thickness, as you talked about the stresses, of course, and it would have a higher surface area. But the biggest question would, in his mind, be seals. So how do you think seals will ensure that they would keep working during and after assembly?
There are no seals. It's all an inch thick welds. So the weld is your seal in this sense. So kind of the tricky part that definitely require a lot of engineering is kind of the temporary latches, that when the arm places one segment next to each other, you have to latch it somehow until the whole sphere is assembled, and then the robot would start welding the individual joints. And I think that a thick, one inch thick weld is a very good seal by itself. So that's the answer there. And regarding the smaller sphere, actually it scales better, kind of the volume to mass ratio scales better the bigger you make it. Of course, the pressure vessel needs to increase in thickness linearly with respect to the radius, so you make it twice as much volume, and you need twice as much mass in your pressure vessel. but then you have the whipple shield, and that doesn't have to increase thickness at all. And that's a significant weight too. So generally it scales, but the bigger you make it, the more bang for your kilogram you get.
Bang for your kilogram. That's a nice new saying that you just invented. We're going to use that. So there are some questions still about the seals, or the in this case welds. Because can you maybe explain in more detail how this welding would be? Maybe like through and through, or is it like a few centimeters deep of a weld? Because the whole package was about 12 centimeters thick, right? And it's only going to be welded from the inside, if I understand this correctly. Can you say that's it, and it's that simple actually, or is there more to it?
That's the magic of electron beam welding, because again, it's probably the only welding method that can do full penetration weld on 30 centimeter, 1 foot thick stainless steel weld. So if you configure it properly, you get completely through, or without burning what's behind it. So that's kind of why this would work, because of this technology exists, and because of the technology force. And generally, the electron beam welding weld. There could be
problems with the effect of heat, and only presenting a really cool concept that a lot of people have never heard about but now know, and of course, but it's more than that. People can actually join your Discord below this video. If you're interested viewer of this stream, any other case related, there are like dozens of the innovation network. So make sure to also click the link to the general Nexus Aurora Discord server and find out what these cool other projects are as well. There's a question about the software that you used during design and the presentation. So you created a cool video. Can you talk a little bit about the software that you used?
Of course, it's basic SolidWorks, pretty much. I learned I'm a kind of software engineer, image processing guy, so I learned SolidWorks specifically for this to model this, some basics of finite element analysis. And once you have the CAD models, even SolidWorks has a bundle that you can buy called SolidWorks Visualize, and you can just grab those CAD models and do renders out of it. It's not really designed to make 2-minute videos. It's designed to make few seconds videos, so it was a little bit of a pain, but that's how it was created. SolidWorks plus Visualize for the rendering.
Yeah, that's very clear. Nice programs for that, at least with great results, great video. Then Shemek Matkowski on our Discord server asks, is the whole process assuming any error margin? It's a broad question. Yeah, I'm gonna maybe Simon can actually contribute.
I'm kind of proud to say that even with this basic design, you have roughly 4x margin for the pressure the module is holding. So there is definitely enough margin, or you can even trim that margin significantly down if you need to save weight. And that's frankly the error margins I was worrying about the most, and I didn't go into analysis of all the possible errors when I'm sure there's thousands of them.
Yeah, but he might also be talking about the error margin in the welding process, or exactly the connections, for example. Yes. I would assume that it is large panels and not that many, but they have to be connected exactly right. But I do feel that you have a method to sort of clamp them together before they start welding, right? Can you maybe explain that?
It's kind of a placeholder method. It needs to be definitely developed. But the idea here, even though the pressure vessels is technically 4.8 millimeter thick, it's the plate. So machine the borders that you weld are 1 inch thick. So if you can make those surfaces of material and like the welding can simulate, but definitely having the connection good enough and having small enough required precision. Yeah, that's definitely one of the concerns and one of the things that have to be figured out during manufacturing, how to make a line very well.
Yeah, and the difficult thing about anything human in space, any human space exploration, is that it takes a lot of time. We know about Bigelow Aerospace and all of those companies that the idea, even if it seems maybe a remark by Simon. He says, or he asks, are there any rails for outside walks provided? Because even though it is created by robotic arms, there'll be a need in the future to repair, for example. Can you elaborate?
Give me 1 second. Again, it's kind of a placeholder. There's a thought given into it. How exactly would it be done? It is debatable, but if I just change my background. These patterns here, the star patterns around the windows, around the sphere. Those are kind of foldable, flippable ladder. I'm not sure what the words for it, the thing that you can grab on if you're an astronaut.
That's great.
So I've given it some thought that you can access it anywhere and it's close enough, but again, the time put into this.
Yeah. Join the Discord server and keep giving Vojtech. That's why he asked all of our help.
That's why I'm here.
Yes, for sure. I'm going to take a look at one comment by Graham Day on the YouTube channel. My biggest concern mechanically is the tolerance stack up that you are going to have to deal with on that sphere. The construction methodology doesn't seem to have a way to deal with a warped panel from launch or another defect. Can you maybe explain if you agree with this concern or if there's any way that you can mitigate it?
Absolutely agree with this concern. And the launch stack and the mounts must be like, I think the only way how to mitigate it is to make sure that you know that you have enough connection points between those stacked panels so they don't get warped. Generally, you just have to make it strong enough for launch, and it's absolutely a concern. Yes.
Then maybe a little bit of a not actually a question in the subreddit engineering porn on Reddit by a mud thug, and he had some questions about joints, but we have already talked about that. But he also thought that this would be a genius way of assembling large dishes for radio telescopes in space. So suddenly a 30-meter diameter reflector doesn't seem out of the question, or maybe 100 meters, 300 meters. What is there to stop you? Have you thought about this kind of telescope? And what are your thoughts on?
I haven't, and it's very interesting. And I could imagine the chamber thing is kind of folded and has to unfold. If you want to scale this up, it might be harder to create the origami unit. It's one of the things that I think is not paid enough attention to, and that's development of robotic arms to make them reliable and cheap enough. Right now, every robotic arm is a one-off and it's extremely expensive. So
we're going to have to mass produce those robot arms, maybe even. Or you could maybe find a way in your idea to actually reuse that robot arm on a next sphere by connecting the spheres and reusing them. Might be an idea. I was also thinking right away when reading this question about the Arecibo telescope that just actually really collapsed after losing some of its integrity before, because these kind of radio telescopes, not the visual ones, but the radio telescopes, they might be a really prime candidate for these kinds of at least first trials of if this technology could work. And you could just create a big stack of those and create hemisphere kind of idea in space. Seems reasonable. If
as far as my knowledge, for radio telescopes, you don't need a solid surface. What you need is a good enough surface that you can kind of have a wire mesh inside.
Oh, for sure. But I think the idea of actually connecting together, that this concept itself creates a partial sphere to create without any disturbances in space. Yeah, that would be really, really awesome.
The idea of placing it to the other side of the dark side of the moon in the crater.
That's gonna have to have it in space. You can actually put it on the lunar surface as well, or Mars, or any other body for that matter, because it is a nice flat pack way to create any spherical or partial spherical shape. So that's really cool. Then a question about radiation shielding by Not Less Grossman on our YouTube video. Can you talk about that in general? Is there any radiation shielding and heat shielding maybe as well?
That's a difficult topic, but you can get away with it because you're doing it in low Earth orbit. So the only way right now the International Space Station is protected is by the Earth's magnetic field and whatever is between the astronauts and the outer space. So the Whipple shield, the walls, and the instruments inside. And that would be no different here, except here maybe on average your walls are a little bit thicker, but still also your main protection comes from the Earth's magnetic field. One of the things that very common question is, would this work around the moon or Mars, or could you use this to build something on the moon? Radiation shielding is one of the things that I haven't given too much priority to. There is no specific design in this to lower the exposure from radiation. So that's why this is a low Earth orbit space station.
For now, but there are of course ways to mitigate these kinds of problems. For example, there are some Starship test designs done already, which showcase that, for example, all the water that you bring with you can be used also as partial radiation shielding, depending on how you place it in the interior. So that might be an option in the future, but of course you're going to work on that with all the people who, after watching this video, will join your Discord server. So if you guys have any ideas about how to mitigate this radiation problem, feel very free to visit orb2.com or check below this video and join the Discord server of Vojtech, who I'm talking to right now on this stream.
Thanks for the plug.
Yeah, I'm gonna keep doing that every 10 minutes. People shouldn't forget. It's a really cool project, and feel free to join. BK553 on Reddit asks, what's the use case for a huge internal volume? Moving around is very difficult without walls. You talked about interior solutions, but I'm going to tell BK553 that he should be creating an interior design and helping out on the Discord channel. But what would you say to this concern?
That if you have interior design skills, please come see us tomorrow. It's only intended to be empty on the beginning, and then once you fill up some rooms, some walls, some structures or things that which for any use and data going around the sphere until the setup crew connects the rest of the utilities. So initially, that would be very basic. Here's the atmosphere, some basic circulation in the habitation module, and that's it. So this would have to be set up. Definitely, there will be a lot of plumbing that will have to be done. But again, the amount and the plumbing might depend on what the customer wants.
Yeah, for sure. We have a few questions actually specifically about something that I also mentioned, this Bigelow. This differs because test on Earth. Can you talk a little bit about that?
Of course. I think that inflatable modules are much better than what we have today, but they are not as powerful as a lot of people think. They are still very heavy. They don't expand that much. I think the expansion ratio is at most 4:1 or 5:1. So it's definitely a big improvement compared to what we have today. But also non-rigid structure is hard to fix, I would say, if something happens. You can just weld patch it up very easily. And here you can end up like solid walls, you can have solid mounting points everywhere, you can have, it's just kind of I don't want to say it, but it's a crude dumb space station, and that's kind of where I would want to be in space, instead of some kind of a
small bus,
very sophisticated Kevlar balloon. Yeah. And to me, this is kind of more scalable, because you can really mass produce this while doing a large inflatable space station. It's a lot of custom work. That's probably hard to automatize.
Seems reasonable enough. Then we have another question on YouTube, specifically about artificial gravity and how the rotation of these kinds of of the Orb2 station, of course, could mean that you could create artificial gravity. Have you thought about that, and would it be able to cope with this idea?
Yes, I thought about it, of course. Who wouldn't? Kind of the idea that I came up with, the simplest way, is that you have two of them. And right now where the ion engines is, on the bottom of the service module, there would be no engines. There would be a hatch to a tunnel that would lead to the other kind of mirrored version with the second Orb2. Then of course you would have to have a module in the middle with the docking, because the only way how you can dock a spacecraft is to have it in the center, the dock in the center of the gravity around which it rotates. So it would pretty much be like there's one ball here, tunnel in the middle, dock, tunnel between them, and dock in the center. And that's the way that it could be done, but it's kind of a step 3-4 on.
Yeah, or the shape itself could rotate along the axis of the surface module. It seems at least to be. Of course, the artificial gravity would only be working on the specific edge of it. But there are other problems with this artificial gravity in this small diameter. Of course, then you get head rushes and all of that blood, or at least a different gravity on your head compared to your feet. Right? That's a problem.
And then you would have good gravity only in a single kind of a ring around which it rotates, and no gravity on the other parts.
And it would be, especially on low Earth orbit, very disorienting if you would do it that way, because you would need to spin it crazy fast with this small. What was the diameter in meters again of the total sphere?
15.6.
15.6. Yeah, that is. I think like this whole idea of tethered starships to Mars, creating artificial gravity. They're talking about at least 100 meters or more, because otherwise you have to rotate very, 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 very fast. And
interesting question is how much gravity do you need to make your life in space comfortable? It might be even less than on Mars, but still you would need a bigger radius to create a comfortable artificial gravity.
We can create a couple of those nice Orb2 stations, connect a great tether or a thrust structure, and test that out in low Earth gravity, low Earth orbit, I should say, before we go and try that out on Mars. So we're going to do that. We're just going to build it. Then the question from JPDLD on the space subreddit is, first of all, very interesting, but he also wonders what other shapes could easily be packed in a small volume and unfolded out, because, of course, you created this shape, I forgot the name, but the gold something.
Goldberg polyhedra, yes.
Exactly. But what other shapes did you consider, for example?
I still think that you can't beat a sphere. Now, how you segment it, that might be very creative, depending what you need. But if I can share the slide again here, you can continue doing, like if you have a very, very big launcher, or you figure out how to start assembling from like 5 different launches to get how to start assembling one space station. You can start creating the same thing with the Goldberg polyhedra, except this time the hexagons will not be identical to each other. In this case they are, so it's simpler, but still the whole philosophy kind of scales up as long as you want a sphere. If you don't want sphere, it's definitely viable, but you'll run into some issues.
Well, one thing that could maybe be an option that is also set by Reasonably Badass, user Reasonably Badass, that's his own name, is that you could, instead of creating a shape with which is spherical, you could also use more of a cylindrical shape. Have you thought about this idea and about how this could also be actually also 2 shapes, right? It's like one curved section, which is curved in one direction only, which also makes the creation and assembly probably a lot easier than the double curved surfaces, I guess, at least. And then you need the domed end caps, of course. Have you thought about that?
Oh, sorry. Yeah, manufacturing like the cylindrical walls, that's done today for rockets. So people know how to do that. I don't see advantages in trying to make a cylinder instead of a sphere, so I didn't consider what's the best way of kind of segmenting it. So yes, it's an option. Again, in cylinder, your hoof stress will be twice as much as in a sphere, so your walls will have to be twice as heavy. Something to consider.
Yeah, that's a good point. Yeah, I'm going to, because some of them are just a lot of positive reactions, but not specifically questions. So we're going to finish it up because we are already talking for 1.5 hours, which is really long already. But just if anyone has any questions left who's watching the live stream or on our Discord server right now, make sure to ask them right now, and I'll try and ask a couple of them. And of course,
I just want to thank everyone for great questions.
Yeah, it's really enjoyable. I'm on page 6 now of question collection, so that's a new record, I think. On the subreddit SpaceX Lounge, there's a question or something that 113. I think that's not the son of. He notes that one thing to note is that Starship doesn't have fairings. Would that mean that?
Build user guide. About half a year ago or so, SpaceX released their for Starship. It's kind of it's 6 pages compared to like 200 pages of all the other launches. So because they assume that they will change a lot, but one of the pages is the payload sizes that they support. So I would assume that the opening, whatever they make, will be large enough for whatever drawing and payload sizes, payload dimensions they drawn there. So hopefully, if you make your payloads to their specifications, it will work. That's my hope. But again, it's SpaceX. A lot of things changes all the time.
That's for sure. Then a question about micrometeor impacts. Of course, you talked about the different layers of the structure, but specifically about meteor impacts, which might even be stronger than space debris. I'm not really sure, but what kind of impact can this structure cope with?
So the Whipple shield on this is, as mentioned here, specifically tested and designed for 1.3 centimeters, so pretty big. It's a nice ball hitting you at 7 kilometers a second, which is the orbital speed. So that can survive that. There are not very many parts of space station that could take that hit. Anything bigger, you have a hole there. There is not much you can do about it. But my hope for the future is, even though the amount of space debris increases, with Starlink there that will be tracking, at least in certain orbits, we'll have so many satellites and we'll be tracking them all the time and avoiding them, that we will get a very good map of centimeter size at least, and larger of debris. So hopefully the passive avoidance will work in the future, partially thanks to Starlink.
And could you explain to me, because you talk about the 7 kilometer per second speed of objects, but if an object is moving exactly the opposite direction, or almost, wouldn't it be an impact of 14 kilometers per second?
It would.
And would it cope with that as well? Or is that like at least 2 times the force, or even the quadruple? I don't know what the equation is in this case.
It's a quadruple the force.
Yeah.
And definitely it's much more problematic. I'm not entirely sure why the testing is done at 7. I think that some probabilistic models generally are more not on the same orbit behind on every side. Just a single orbital speed, and I think that cannot do. That's a ballpark.
Yeah, but I think the interesting figure that you have here is we have a good statistic, and that is the ISS and the amount of impact that has survived, and this one's going to be a lot stronger if I understand your talk.
As strong as it is. Yeah, ISS the pressure was not penetrated a single time, but from the outside of holes. So
yeah. I think for now we'll stay in this Discord chat where I see a lot of other questions from our own Discord server at Nexus Aurora coming in, but we'll talk about that after the stream. For now,